Alright, welcome. In this video, I'm going to be working through BC Quiz 12.4 Form H. This is a free response quiz about Taylor series, and so the first one's talking about the first three non-zero terms and the general term of the Taylor series for cosine x centered at x equals 0. Alright, that's just one that we're supposed to know. It's the Maclaurin polynomial for cosine x. That's going to be, okay, it starts with, let's just say, cosine of x is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. That's in three non-zero terms. The general term is negative 1 to the n, x to the 2n divided by 2n factorial. Okay, and that's something we just need to know. Okay. And we're going to write the first three non-zero terms in the general term of the Taylor series for f at x equals 0. And f is x squared multiplied by cosine of 2x. So I'm going to start by working with cosine x, replacing x with 2x, so I get cosine of 2x, and then I'll multiply by x squared. Okay, so cosine of 2x equals, okay, well, wherever I see x, I'm replacing it with 2x. So 1 minus 2x squared divided by 2 factorial plus 2x to the 4th divided by 4 factorial. Okay, I'm going to say, and the general term, so that'll be negative 1 to the n, 2x to the 2n divided by 2n factorial. Okay. And yeah, okay, so f is going to be just all of this multiplied by x squared, which means it's all of this multiplied by x squared. And I always forget to do this, but I should probably put, like that, indicate that it is like the full series and that that is an equality, but I don't think I'll need to worry about that so much. I'm thinking that actually, because I'm gonna eventually have to anti-differentiate, I do not want to leave the 2x to the 4th and that stuff and have an x squared attached to it. That's not going to be the way I want to go. Okay, we can leave the general term like that if we want. If you feel like that's safer for you, that's fine. I'm going to go in and I'm going to say, all right, that's 1 minus 4x squared over 2 factorial plus 16x to the 4 over 4 factorial. The general term is really all I did here was just take that 2 to the 2n, x to the 2n divided by 2n factorial. Okay, meaning that f is, I'm going to just distribute an x squared to each of these terms. So it'll be an x squared minus, okay, 4x squared times x squared would be 4x to the 4 divided by 2 factorial. Plus, okay, when I distribute an x squared to this thing, I'll have x to the 4 times x to the 2. That's going to be x to the 6 divided by 4 factorial, all the way up to negative 1 to the n, 2 to the 2n, x to the, I really just added 2 to the power of each x. So I'll have x to the 2n plus 2. I'm still dividing by that same 2n factorial. Okay, that's f. Now we're going to write the first three non-zero terms of the Taylor series for g. And going back up to here, g is an antiderivative for f with respect to x, okay? And it's going to be the antiderivative with g of 0 equals 0, right? Because if I plug in 0 right there, I'll have the integral from 0 to 0, and we know that comes back to 0. Okay. So I'm going to anti-differentiate this thing. And I'm going to say it's going to be c plus 1/3 x to the 3rd, 4, so minus 4x to the 5 divided by 2 factorial and 5, and plus 16x to the 7 divided by 7 times 4 factorial. It didn't ask for the general term, so I'm not gonna write it. First three non-zero terms, I'll definitely have it. Okay, at x equals 0, I know that it needs to come back 0, so 0 plus 0 plus 0 plus c needs to equal 0. That means that c is going to equal 0. So I'm going to just get rid of that. And there it is. All right, then let P4 be the 4th degree Taylor polynomial for G. I don't see a 4th power term. Okay, that must be a mistake. I'm going to use the Lagrange error bound along with the information in the given graph to find an upper bound for P's the fourth real polynomial with 0.1 plugged in minus g of 0.1. Okay, that's the error. Okay, I think we're just going to take it on faith, even though there's no x to the fourth term. I guess the fourth degree polynomial is just 1/3 x to the third, and plus 0x to the 4. We know that if we use a fourth degree polynomial for g, that error is bounded by the fifth power term. And we're going to use the Lagrange error bound because it told us to, and there's a picture of the graph of the derivative, so that's a hint that you're going to use Lagrange error bound also. We're going to say it's the maximum of g's fifth derivative, or I guess the absolute value of g's fifth derivative, divided by 5 factorial, times the absolute value of 0.1, that's the value I plugged into the polynomial, minus 0 is the centering x value, to the fifth power. Okay? And we're interested in the maximum value of g's fifth derivative between x equals 0 and x equals 0.1. And, okay, I'm going to go over here and I'm going to look at it. Okay. At 0.1, okay, the maximum possible value is right here, which looks like 6, 7, 8 would be the upper bound for it. Okay, so this is probably not representative. The ones I've seen from the College Board, typically the number that you're supposed to use is printed on the sheet of paper, but it's got a grid on it, so you can tell that that graph is below or at 8 all the way through x equals 0 to x equals 0.1. Okay, so the maximum value I'm going to pull right here is going to be 8. Okay, so I'll have less than or equal to 8 divided by 5 factorial times 0.1 to the fifth power, and that's going to be just find an upper bound. Okay, well that's the upper bound, it's the error bound. Okay. All right. I'm back. Here we've got, suppose capital G has derivatives of all orders, and the Taylor series for G around x equals 3 is given by this. Okay, we're going to find the 8th derivative of G at x equals 3. So, I mean, I kind of see two ways to go here. I could either say, okay, I'm pretty sure I can figure out what the next term would be. I think the next term would be, just looking at the pattern, each time I'm getting 2 more powers of x minus 3. So I'm going to have x minus 3 to the 8 divided by 14. On the other hand, I could see that this is where n is going to equal 4 because I need that 8th power term to get my 8th derivative. Okay, so it's going to be negative 1 to the 4, x minus 3 to the 8 times, what would that be? 4 times 3 is 12 and 2 is 14. Either way, you're going to have x minus 3 to the 8 divided by 14. Okay, so I'm going to say x minus 3 to the 8 divided by 14 equals g's 8th derivative at 3 times x minus 3 to the 8 divided by 8 factorial. Okay, so I'm going to cross off the x minus 3 to the 8th power, because that's not telling me anything about the derivative. And now I know, okay, the 8th derivative divided by 8 factorial is 1 over 14, so I know that it's just going to be 8 factorial divided by 14. So I'll just write that in over here. And then I'm going to find the first 4 non-zero terms in the general term of the Taylor series for g prime of x at x equals 3. Okay, so what I'm going to do is I'm going to take the derivative of these terms and the general term, which is right here, and I'm just going to report that. Okay, so the first 4 non-zero terms, that's going to be a 0 term because the derivative of a half is 0. So I'm going to have negative 2/5 x minus 3 to the first plus 4/8 of x minus 3 to the third minus 6 over 11 times x minus 3 to the 5. Okay, this is only 3 non-zero terms, so I need that 4th term, 8 over 14 x minus 3 to the 7. Okay, reduce the power by 1. Now, I'm going to take the derivative of the general term, okay, but I don't really have enough room to write it, so I'm just going to say these are the first 4 non-zero terms, then the general term is going to be, okay, take the derivative of this thing. Well, we know how to run the power rule. We bring the power down, so I'll have negative 1 to the n times 2n Then I'm going to subtract 1 from the power, so that's x minus 3 to the 2n minus 1. And then we're still divided by 3n plus 2, and that didn't really change when I administered the power rule. I still got those same denominators that I had before, 5, 8, 11, 14. Okay, so I'm going to leave the denominator the same. Okay. Now, the given Taylor series, evaluated at x equals 7/2, is an alternating series whose terms decrease in absolute value to 0. All right. Like I've said before, when you see that in the statement of the question, that means you're about to be doing the alternating series error bound. So the approximation for g of 7/2 using the first two non-zero terms of the series is 3/10. Okay. Cool. So that this approximation differs from g of 7/2, like the true value, by an amount less than 1 over 100. So we're just going to say, all right, if we're using the first two non-zero terms, the error is going to be no more than the absolute value of the next term. Okay. Which would be, okay, if I used for g, okay, and that's this one right here. If I use the first two terms, then the third term is the error bound. Okay, and I'll take the absolute value of x minus 3 to the 4 over 8. Okay, x is 7/2, so 7/2 minus 3 is 1/2 to the 4th divided by 8. Okay, 2, 4, 8, 16. Okay, and then 3 more is 32, 64, 128. So I'm going to say that this is 1 over 128, which is definitely less than 1 over 100. Okay. And then the radius of convergence of the given Taylor series is 1. Determine the interval of convergence and justify my answer. I can do that. Okay. So I know it's centered right here at 3, so that means it's going to reach out to 4 and back to 2. Okay. So the interior of my interval is 2 to 4. But I need to check the endpoints as well to see if my series is going to converge at 2 and 4, because the ratio test, you know, if I ran it, it would tell me that the radius was 1, but it doesn't tell me what's happening at 1 unit away from the centering point, right? When L equals 1 in the ratio test, it's inconclusive. We don't know, it could go either way. So we're going to do a little bit more analysis. At x equals 2, I'm going to go back, and we can plug into this, and I think that that's what I'm going to want to do. I think I'm going to want to plug directly into this formula, just the series formula. Because you could say that's 1/2. When I plug in, what was it, x equals 2, I'll have -1 squared is +1, -1 to the 4 is also positive. So I mean, it's always going to be positive. So it will keep alternating. Maybe you run the alternating series test on it, but I think, I mean, I'm going to have to run the alternating series test anyway. But I think it's actually easier to just look at, all right, sum from 0 to infinity, -1 to the n that was already there. 2 minus 3 to the 2n is going to be a -1 to the 2n. Okay, divided by 3n plus 2. Okay, well, -1 to the 2n, that's -1 to an even power, always. Which means that's always +1. Okay, so I'm going to just kind of say, all right, just get rid of that, say it's not even there, because it's a 1. You know, multiplying by 1 doesn't do anything, so I'm just going to kind of act like it's not even there. I'm going to say this is an alternating series. This is going to converge because it's alternating and bigger on bottom, right? But that's not what we're going to say. We're going to say this series alternates. Okay, the absolute value of the terms, which is 1 over 3n plus 2, is decreasing. And the limit of the terms, okay, so that's -1 to the n divided by 3n plus 2. That limit is 0. These things together tell me that it converges at x equals 2. So I'm going to include 2 in my interval. Okay. At x equals 4, I'm going to have the sum from 0 to infinity of -1 to the n. 4 minus 3 to the 2n is 1 to the 2n. That's another thing where it's like power of 1. It's just going to be 1. So I'm not going to include it. And 3n plus 2, I'm going to say converges for these same reasons, because it's the same series. Okay. And that means I'm going to include that in my interval of convergence, and I will clearly indicate that that is the interval on which the Taylor series is going to converge. Okay, that's all the problems. This is a good selection of a couple of free response problems, and I think honestly it's pretty representative of what I might give you on a Taylor series test. One thing I was going to go back to that I should have mentioned it, I'm not able to just go back and find the spot and add something to the video, but something I didn't actually point out here that I'm realizing is that g's fifth derivative, this is not what's pictured here, right? This is the picture of f's fourth derivative. Okay, so I'm going to do a little more. Yeah, I'm only 16 minutes in, so graph of f's fourth derivative. Okay, but I also know from up here that g prime equals f. So as a result, if g prime is f, then g double prime equals f prime. G triple prime equals f double prime. And maybe you see the pattern, but I'm going to be really explicit here. G's fourth derivative is f triple prime, and g's fifth derivative, which is what I'm interested in, is the same as f's fourth derivative. So that's why, even though it seemed like the wrong graph, it was the right graph. It was, and so that's actually the same as the maximum of f's fourth derivative, which I ran on the graph without even saying anything, which is definitely my fault. Okay, and I hope you'll forgive me, and hopefully this helped. Thanks for watching.